Okay, thank you very much, everyone. Sorry for the bit of a delay. As we kick off this track on expanding your frontiers, I'd like to give me great pleasure to introduce Dr. John Lewis. He is a principal investigator for science at the University of Arizona's Space Engineering Research Center for the utilization of local planetary resources. And I think that name itself says something important about thinking that's occurring about using the solar system's resources. We start off with something local and hopefully relatively easier to get to than others. Dr. Lewis has a doctorate in geochemistry and physical chemistry from UC San Diego. He is an honorary lecturer at the American Astronomical Society. He has received awards from the American Geophysical Union and the Exceptional Scientific Achievement Medal from NASA in 1983. With that, I'd like to introduce Dr. John Lewis, who will talk to you about asteroid resource utilization.
While all of you were gorging on the banquet, the luncheon meal, I was very conscientiously sitting here in this room alone, working on my notes. So you all arrived late. Consider that I started 10 minutes ago. I'm going to talk to you a bit about several different ways of using non-terrestrial resources. And I think that it should be fairly clear that the principal use, and especially the most important near-term use of non-terrestrial materials, is in space in support of large-scale space activities to lower the cost and expand the scope of future space activities. Second possibility is that certain non-terrestrial resources may have sufficiently high intrinsic value so that they'd be worth returning to Earth. I will say relatively little about that, although it is indeed an interesting aspect. I will concentrate principally upon in-space uses of non-terrestrial materials, and the following requirements must be met. The materials we talk about must, first of all, occur in significant quantities in objects which are relatively near to Earth, meaning the Moon, the Earth-crossing asteroids, the satellites of Mars, and the surface of Mars. In other words, areas where there will be where there is a real prospect of near-term, large-scale human activity. Third, the resources must be, in some fairly straightforward way, extractable from the body on which they occur. And fourth, the body on which they occur must be energetically accessible from Earth, and near-Earth space must also be energetically accessible from that body. So those requirements narrow down the scope and narrow down the field quite a bit. I shall spend most of my time talking about the ramifications of finding water on nearby objects in space, extracting water and using it, especially in support of propulsion systems. But I shall also have some things to say about native ferrous metal alloys, iron meteorites, and iron meteorite material derived from these nearby bodies. Now, I think the simplest way of getting into this is to start with what everyone is familiar with, namely the asteroid belt, and narrow down the scope of our discussion to something which is more accessible. The asteroid belt has approximately 5,000 known and cataloged asteroids in it. These asteroids are all at least 1 kilometer in diameter, and our catalog of these asteroids is woefully incomplete because many of them are extremely dark, have very low albedo or low reflectivity of visible light, and are therefore extremely hard to find. And if they are in the belt, they never get close to Earth. They're always a couple of astronomical units away from Earth or more. The real number of kilometer-sized and larger bodies in the asteroid belt is probably 30 to 50,000. I'm not going to be talking much about the asteroid belt. It's too far away. There is a subset of asteroids, some 208, I think it is, are known as of last Monday, which are called near-Earth asteroids or Earth-approaching asteroids. These are in orbits that bring them into the inner solar system where they cross the orbits of one or more of the terrestrial planets. The large majority of these actually cross Earth's orbit twice on each trip around the Sun. There are only 200 of those known versus about 5,000 belt asteroids. Nonetheless, these Earth-approaching asteroids are in our own backyard. Some of them have been discovered within a few lunar distances of the Earth. In fact, one of them, a little over a year ago, was tracked down to a distance of 160,000 kilometers from the surface of the Earth, well within the Moon's orbit. These objects frequently pass through the Earth-Moon system and are from time to time the closest objects in the solar system to the Earth. They also represent samples extracted from the asteroid belt by some processes that are partially understood but not fully understood. Basically, certain locations in the asteroid belt have orbital periods that are harmonics of the orbital period of Jupiter. Therefore, the tidal or the gravitational accelerations on these bodies get pumped up. They repeat themselves from time to time. They don't cancel out. They don't average out from one orbit to the next. And these objects get pumped into eccentric orbits which come into the inner solar system and cross the orbits of the terrestrial planets. These near-Earth asteroids don't stay in such orbits for very long periods of time. They are in a high-traffic environment in here. They're constantly crossing the orbits of Mercury, Venus, Earth, and Mars, and their orbits will be constantly perturbed, and they are, in a sense, chaotic orbits. They are not stable over long periods of time. A typical near-Earth asteroid will live for 10 to the 7th, 10 million years, to 10 to the 8th, 100 million years, before colliding with one of the terrestrial planets. The most likely fate for an Earth-crossing asteroid is that it will eventually collide with the Earth. The second most likely fate is that it will collide with Venus. The third most likely fate is that it will be perturbed by the terrestrial planets into a Jupiter-crossing orbit and be kicked out of the solar system altogether. Okay, so there is a means of providing belt asteroids to the vicinity of the Earth. To give you an example now, let's suppose that you as an individual had access to the following resources. 100 million tons of iron, 10 million tons of nickel, 1 million tons of cobalt, 100 million tons of water, 10,000 tons of precious metals. Okay, what could you do with resources like that? Well, in the asteroid belt, if you divide the known resources of the asteroid belt up evenly among 10 billion people, that's your share. So the idea that there is a resource problem is absolute nonsense. Most of these resources happen to be inconveniently located. So there's a serious economic question and a serious intelligence question as to whether we can devise profitable ways of exploiting these resources. I should point out that resources of this magnitude, if they are recycled and used in a steady state, could support a population approximately 100 million times the present population of the Earth. Now, clearly they're not all going to live on the Earth. Now let's talk a bit about what these materials are. We need to know what the raw materials are, where they're located, and how to get access to them. Our first source of compositional information on asteroids is for meteorites that fall on the Earth. If I can have the first transparency, please. You'll see here, this is designed for a smaller room. I had no idea how big the room would be. This is a listing of the basic categories of meteorites. Stones, stony irons, and irons. The stones make up 96% of all the known meteorites. The stony irons, 1% of all the known meteorites, and the irons, about 3%. The irons are about 99% metallic iron, nickel, cobalt, platinum group metal alloys with traces of sulfides, phosphides, carbon, and so on, and graphite. Stony irons are about half stone material and half iron like these iron meteorites. And the stones are subdivided into two groups, the chondrites and the achondrites. The chondrites are primitive, ancient, unmelted, undifferentiated, raw material from the era of the formation of the planets. They represent essentially the materials of the Earth or the other terrestrial planets if you were to run the entire planet through a giant blender and homogenize them. The achondrites are the results of melting and differentiation. They are from geochemically melted, differentiated, evolved asteroids. Or some achondrites are from the moon, or some are from Mars. They're the results of igneous processes on the moon and Mars. The next transparency, please. We now turn our attention to the primitive meteorites, the chondrites, the ones that have never melted and differentiated. Here's the breakdown of them according to type. They have a wide range of oxidation states, from the enstatite through the ordinary chondrites to the carbonaceous chondrites. These are all primitive bodies. All the chondrites are primitive materials. The enstatite chondrites are so chemically reduced that they contain no oxidized iron, no iron oxides at all in them. They even contain some reduced silicon dissolved in the metal phase. If you can imagine extracting a piece of iron from one of these meteorites, it may contain up to several weight percent of elemental silicon dissolved in the iron. So they're chemically amusing. The ordinary chondrites are chemically very similar to the average composition of the terrestrial planets, and they look like the raw material of planetary formation. They dominate the chondrites and make up 87% of all the known primitive meteorites. The carbonaceous chondrites are highly oxidized and very rich in volatile materials. They look like the raw materials from the outer part of the asteroid belt, distant from the sun. The carbonaceous chondrites contain up to 20 weight percent of chemically bound water in the clay minerals and hydrated salts and so on. They are dominated by clay minerals. They have magnetite. They have organic polymers making up as much as 6% by weight of their total mass. These carbonaceous chondrites make up only 9% of all the chondrites and only about 8% of all the known meteorites. Now, briefly, the next transparency shows you how the densities of these different kinds of materials compare to known asteroids. And you see the most volatile rich Ci chondrites, the C2 or Cm chondrites, somewhat higher density and lower concentrations of volatiles in them. And on the right, the C3 chondrites, which are more like ordinary chondrites, compared to the densities of three of the largest asteroids. Why these three? Because they're the only three asteroids for which we have useful estimates of their mass. It's very hard to find out the mass of an asteroid unless you have a spacecraft flyby. And even the mass of Gaspar is not yet known after the Galileo flyby. The densities of the number of the largest asteroids, two of the three largest asteroids are comparable with those of very volatile rich meteoritic material. And Vesta, which looks like a piece of achondrite, has a density which is relatively uncertain, but which spans the densities of achondritic meteorites. And the reflection spectrum of Vesta is also the reflection spectrum of an achondrite. So it looks like melted and differentiated material that has lost its metal content. The metals have been separated from it and are no longer present on the surface. Well, that's now let's move on to the next transparency. For the achondrites, these are the melted and differentiated meteorites that have been melted by radioactive decay or other heat sources and have separated according to density. And what we have here is the silicate portion of it. Very low concentrations of metal in them. And these are relatively minor resource use, and this is mostly here for completeness' sake. The next transparency, please, for the iron meteorites. The irons are of apparent tremendous resource interest because they have very high market values: iron, nickel, cobalt, platinum metal alloys. There is an iron meteorite known among the near-Earth population. It is an asteroid with the euphonious name of 1986 DA. And this asteroid is about 2.3 kilometers in diameter. It's made of iron meteorite material. It has an enormously high reflectivity to radar, and has been studied by radar from Earth. and has in the visible and near-infrared the reflection spectrum of an iron meteorite. This is the smallest known metallic or M-type asteroid, smallest known. If it were out in the belt, we would have a hard time finding it because it's only 2.3 kilometers in diameter. This asteroid contains roughly 30,000 about $20,000 billion worth of nickel, and about $25,000 billion worth of platinum group metals. This is the smallest known metallic asteroid. So there are resources in near-Earth space which, given a chance, may very well descend upon Earth and create a giant impact crater, which dwarf all of the accessible iron, nickel, cobalt, and platinum metals in mineable reserves in the Earth's crust. You probably know that nickel and platinum group metals have been for many years mined from the Sudbury structure in Ontario. The largest source of nickel and platinum metals in the free world has been Sudbury. Sudbury is an astroblem. It is an impact crater. So it's sort of ironic that we're already using asteroidal materials and didn't know it. Finally, the next transparency tells us a little bit about stony irons, and they're about half iron meteorite material and about half achondrite type material. They have different structures. These are siderites and pallasites. They have about the same overall composition. Okay, these are the materials that fall on Earth. And the statistics that we derive from our meteorite collections is that about 8% of all of the meteorites known on Earth are volatile rich. They're full of water, carbon, nitrogen, and other interesting materials, organic polymers, clays. Roughly 40% by weight of one of these meteorites is easily extractable volatile materials. So think of them as being a sort of a form of imprisoned water and carbon that's mineralized so that it makes it easier to handle. Now, there is a problem using these statistics to apply to the near-Earth asteroids. We know that virtually all of these meteorites come from near-Earth asteroids because they're in Earth-crossing orbits. They couldn't land on Earth if they weren't. They're fragments eroded off of nearby asteroids. But there's a serious problem. If you look at the meteorites that are found on the ground after having been here for goodness knows how long, and compare them to the meteorites that are observed to fall, the old meteorites that are accidentally found long after falling, the so-called finds, have very low proportions of these fragile, volatile-rich meteorites. The ones that are observed to fall have much higher proportions of them. And the reason is very simple, that if a carbonaceous meteorite falls to the surface of the Earth and is not observed at the time of its fall and is not harvested quickly, the first time it rains on it, it goes away. It's cemented together by water-soluble salts. It's very similar to a chunk of mud from the bottom of a river. It's full of organic matter and clays. You can imagine wadding it together into lumps like a snowball, clayey lumps that stick together. Now imagine sitting one of these on the ground and letting it rain on it. It goes away. So we know that this underestimates the real abundance of carbonaceous material in near-Earth space. So let's put these aside and say at least 8% of the nearby asteroid material is volatile rich and appropriate for making water and other rocket propellants, life support fluids, and so on. Now let's turn to spectroscopy, spectroscopic studies of the near-Earth asteroids. About 50 of the near-Earth asteroids have been discovered by astronomers, have been studied by astronomers in the visible and near-infrared to find out what minerals are present on them. And what they find is that 25% of all of the near-Earth asteroids look like laboratory samples of carbonaceous meteorites. They're extremely black, very, very dark material, typical of the organic polymers you find in carbonaceous meteorites. So 25% of them are black and carbonaceous. Well now, the problem with this is that in order to get the reflection spectrum of a near-Earth asteroid, we first have to discover it. But the process of discovering a near-Earth asteroid discriminates very strongly against finding the darker ones, because we search for near-Earth asteroids in visible light. If we search in visible light, this means that the darker ones have to be much larger in order to be found. And we don't have anywhere near a complete collection, a complete sample of even the kilometer-sized black near-Earth asteroids. So let's make some reasonable estimates. We know about the capabilities of the instruments that are searching for asteroids nowadays, so let's make a guess. Let's estimate, based on the capability of those instruments, what fraction of the near-Earth asteroids really are black and carbonaceous and full of volatiles. And the answer comes out about 50%. So we've gone from 8% to 25% to about 50%. Now we turn to the pure theorists, the ones who study the evolution of cometary orbits. And they have a most interesting story to tell us. As you know, many comets are in short period orbits. There are about 700 comets in short period orbits, which orbit about the Sun after having interacted strongly with Jupiter. They've been perturbed into orbits that come close into the Sun. If one of these comets makes countless thousands or even millions of passages close to the Sun as it orbits about in an eccentric orbit, it will lose ices from its outer regions. The surface will be heated by the Sun. Volatile materials like ice will evaporate and leave behind a deposit of black dust. Comets are dirty snowballs. They're mixtures of carbonaceous dust and ices. The theoretical models that have been done to describe the evolution of these comets suggests that they give off the ices in the outermost few meters of their nucleus. But beyond that point, the solar heating is ineffectual at reaching the ice. The ice is now too deeply buried to be affected by passage through perihelion close to the Sun. As a result, the evolution of the comet stops, and it remains with a large ice-rich nucleus buried at a depth of 5 to 10 meters beneath a layer, a lag deposit as geologists call it, of fine black dust, which is a wonderful insulator. It's in a hard vacuum, little dust, fluffy dust particles touching each other. It's an incredibly good insulator. Their estimate is that the rate at which short period comets shut down and ceased looking like comets would be just about right to provide 50 or 60% of the near-Earth asteroid population. Now this means that as many as half, maybe even a little more than half of the nearby asteroids are in fact pseudo-asteroids. They are extinct comet cores with huge masses of water ice only a few meters below a fluffy insulating surface. Here's an extraordinary resource in our own neighborhood, something we don't have to go out to the outer part of the asteroid belt to reach, but Jupiter's gravity has thrown it into an Earth-crossing orbit. And now it's waiting to be used up, or if we fail to use it up, we pay the consequences. Most likely, it will strike Earth. Now, do we have the next transparency, please? Gene Shoemaker put together a population description of the near-Earth asteroids a few years ago. Here we have the relative numbers of the asteroids on the left side of the diagram, and their magnitude across the bottom, or their diameter in kilometers across the top. And the black dots represented observational statistics as at the time he did this in about 1986. Notice that the predicted population, which is the dashed line, is much higher, and this means that our discoveries were very incomplete for all bodies fainter than about 14th absolute magnitude. Nothing surprising about that. And his estimate of the total population is that dashed line at the top, and you'll notice that there's an increase in numbers as you go down to smaller sizes, and when you get down to sizes of 3 or 4 kilometers, Shoemaker had the plot bending over so that there would be so that the rate of increase of numbers towards smaller size was less than it was at larger size. This was done in an attempt to explain the cratering statistics on the moon, but objects down toward the left side of that diagram are so small that what they do indeed make craters on the moon, but these craters are hard to extricate from secondary craters made by chunks of rock ejected by giant impacts on the moon. So the statistics are relatively difficult. Anyhow, that was the accepted wisdom as of 1986. Since then, the number of known near-Earth asteroids has more than tripled. It's gone from 64 to 206, or 208. Can't keep track. I'll flash on here some completely unreadable graphs that will show you how many there are. And these are highly characterized. Their orbits are well known. Every one of these has a well-known orbit. Look at that. Page on through. Just page on through the next couple of charts. This is what we've got to work with, folks. This is what we have that are passing through near-Earth space. The database is available to anybody who wants to get a copy of it. Just write to me at the Lunar and Planetary Lab at the University of Arizona, and I'll send you a copy of it. The next one. Each one of those represents typically a kilometer-sized object. The biggest one on that list is 30 kilometers in diameter. It raises the orbit of Mars, it doesn't cross Earth. The smallest known near-Earth asteroid as of a few years ago was about a kilometer in diameter. But in the fall of 1991, the Spacewatch camera at the University of Arizona became operational. Spacewatch is an extraordinary instrument. It uses a dedicated 36-inch telescope. Now, 36-inch telescope, that's a baby. That's a real small telescope. It uses a 2,000 by 2,000 CCD detector array, just like in a solid-state video camera, except this is the biggest commercially available CCD detector array in the world, 2,000 by 2,000. It images the sky, steps along, looks at the sky, then goes back about an hour later and re-images the areas that it just looked at. It develops a fully computerized star catalog based on the first image. When it re-images the same area, it looks for objects that have moved. If it finds them, it comes back at the end of its night's observations and re-images the same area again and locates the object. With those 3 points, you can readily and accurately project where it will be found the next night. This is done automated, completely computerized. People sit there in the dome alongside it and drink coffee while the program whirs. Spacewatch has achieved a discovery rate which is approximately twice as high as the world discovery rate before Spacewatch came along. And Spacewatch is discovering, because it's very sensitive, it's discovering small asteroids and close asteroids. 3 times it has discovered the closest asteroid to Earth ever found, and they keep getting closer and closer. It has found the smallest asteroid ever discovered, 8 meters in diameter. Now you see, why would we worry about an 8-meter object? Very simple answer. Hiroshima. That's 20 kilotons of explosive power. Now these new asteroids, the new ability to discover these asteroids is really providing us with exciting and useful new information. We used to be unable to see anything smaller than a kilometer in diameter using astronomical techniques, and there was a gap from 1 kilometer size right on down to about 1 meter size in our understanding of the abundance of bodies out there. 1 meter sized objects we have pretty decent statistics on. The simple reason for that is that these are common enough so that photographic networks that search for meteorites entering the atmosphere see a fair number of 1 meter objects. And we know how many there are. We know what the rate at which they hit the Earth is. But between 1 meter and 1 kilometer, there was nothing until Spacewatch came along. And now Spacewatch is providing data on 8 meter to 1 kilometer sized objects. The gap has nearly vanished. Now let's take a look at what Spacewatch has found. First of all, let's do the next transparency. Spacewatch has increased our number of near-Earth asteroids to over 200. I read that, you see, this is April 15, so there are only 203 of them. You have to work hard to keep up to date. This compares the spatial distribution of all the asteroids on the left. See that outer circle is the orbit of Jupiter, and the inner circles are the orbits of the terrestrial planets. And on the right, we have the near-Earth asteroids, known as of April 15th. And notice where they are. They go right on into inside the orbit of Mercury. Notice also that these near-Earth asteroids do go out almost to Jupiter sometimes. In order to be on that diagram on the right, the asteroid must, at perihelion, come into the interplanet region. But notice that at this moment in time, some of them are out beyond 4 astronomical units from the Sun. This means that if you establish a base on a near-Earth asteroid, celestial mechanics will automatically take that base out to and through the heart of the asteroid belt. So we have a transportation system and a propellant mine on each of the carbonaceous near-Earth asteroids that has been conveniently shunted in to make it accessible to Earth, and it provides us with transportation out to the heart of the belt. So I said I was not going to talk at first about the resources of the asteroid belt because of its inaccessibility. I was going to talk about near-Earth asteroids. I did. The near-Earth asteroids represent the key to access to the belt. The Spacewatch program has discovered numerous new asteroids. Some of them are given here on the next transparency. The first year of activity of Spacewatch, the world discovery rate for near-Earth asteroids was about 12 per year before Spacewatch came along. That's the first year of operation, September 90 through September 91. And if you're close enough to read some of the information on there, you'll find that some of these asteroids have orbits that are fairly similar to Earth's with low inclinations and low eccentricities. Some of them go quite a ways out. And the next transparency gives us the data from September 91 up through early May of this year. This is how the discoveries are going. I would especially point out asteroid 1992 AD on there. Its perihelion distance, closest approach to the Sun, is 8.7 astronomical units. In other words, it's close to Saturn, and its aphelion is 32 astronomical units, close to Neptune, and it's a diameter of 140 kilometers. This is not a near-Earth asteroid. It's the only one on there that isn't. It was discovered by the same system. It is a Chiron-like object, like a giant and a huge asteroid, orbiting across the orbits of the Jovian planets. It's relatively straightforward to do a model of the orbital evolution of this body, and what you find is that over a period of 1 million years, this orbit changes chaotically because of perturbations by, at the moment, Saturn, Uranus, and Neptune, but also Jupiter, because it frequently gets perturbed into a Jupiter crossing orbit. According to the models that have been run, this object sometimes wanders into an Earth crossing orbit. 140 kilometers in diameter. It would have approximately 1,000 times the explosive yield of the Cretaceous extinction event. It has an explosive equivalent of about 200 billion tons, 200 billion megatons, 200 billion megatons of TNT. By comparison, an all-out World War III is about 17,000 megatons. It would be nice to keep track of these bodies. It would be nice to discover them, find out how many they are, where they are, and predict their orbits. If you don't follow my logic, ask me after the talk. Okay, now using the Spacewatch discoveries, here's what we found. The next transparency, please. This is a frequency mass diagram for these bodies. The solid line in the lower part of the diagram is a simple extrapolation of the size frequency relation for main belt asteroids on down to smaller sizes. The smallest observable near-Earth asteroid is around 10 to the 9th kilograms. So anything to the left of 10 to the 9th or 10 to the 10th on there is an extrapolation. And that solid line is an extrapolation of belt asteroid statistics. The black boxes on there are Spacewatch discovery statistics. And what we're finding is that objects with sizes of about 100 meters in diameter are 30 times as abundant as we used to think. Objects with diameters of 20 meters are, let's see, about 100 times as abundant as we used to think. And when you get down to a few meters diameter, presumably there will be a smooth transition from those black boxes to that dashed curve in the upper left, because that's the fireball data on meter-sized and smaller objects. So those objects are going to be 1,000 times as abundant as we previously thought. Our ideas about the abundances, the frequencies of kilometer and larger sized asteroids were pretty good, but Spacewatch is showing us that we were totally wrong about objects much smaller than a kilometer. And we're talking here now about impactors that are in the 100 megaton down to 10 kiloton explosive range. And we underestimated their abundance by a factor that ranges, as you see here, from about 30 to 1,000. Well, this might be good to know. Unfortunately, it's very hard to develop a complete catalog of all these small bodies, because there are, after all, not only huge numbers of them, we knew that already, but there are 1,000 times that huge number of them in reality. So we have approximately 1,000 kilometer-sized near-Earth asteroids to account for. And when you get down to 100-meter-sized objects, the number is near 1 million, between 500,000 and 1 million. When you get down to 10-meter-sized objects, the number is on the order of 1 billion. So that would represent a stupendous task to discover all of those. Now, let's talk a little bit about using what we know about the compositions of the near-Earth asteroids and their orbits and their numbers. Let's talk a little bit about using material from them. Okay, next transparency, please. There is an energy cost associated with going from Earth orbit, let us say departing from the space station, never mind whose space station, and traveling out to a near-Earth asteroid. On the left side of this diagram is the delta V requirement, the velocity change requirement for a rocket departing from the space station to travel out to and land on the surface of these other solar system bodies. The names and numbers on there are the identities, the labels of various near-Earth asteroids. And I call your attention at the bottom, Earth escape velocity. That's the velocity required to get from the space station out of Earth's gravity well into independent orbit about the sun. And at the top of the diagram, the delta V required to fly from the space station to a soft landing on the surface of the moon, about 6 kilometers per second. All of those asteroids indicated on there, plus several other new ones that I haven't had a chance to add yet, are more accessible than the moon. An expedition taking off from the space station to travel to the surface of the moon would have excess propulsion capability to land on all of those other near-Earth asteroids that are listed. Roughly 1/4 to 1/5 of all the near-Earth asteroids are energetically more accessible than the moon for expeditions outbound. That's because they have very small surface gravities. You don't have to burn a huge amount of propellant in order to land soft. You can rendezvous and dock with them and then touch down gently. You cannot do this with the moon. If you come to a stop near the moon and coast down to the surface, you hit the surface at over 2 kilometers per second and you get thoroughly vaporized. Now, on the right side of the diagram is the projected number of near-Earth asteroids in each of those velocity boxes that are larger than a kilometer in diameter. You'll see that there are 134, I think it is, kilometer-sized near-Earth asteroids that are more accessible than the moon. Why did we go to the moon? We didn't know about these bodies. We went to the moon. And besides, it's a shorter trip to the moon and back. It's a week out and back. With these bodies, you typically have to go out for a period of several months outbound and several months back. It's like a mission to Mars. Unless, of course, you catch one as it passes through the Earth-Moon system, in which case it's closer than the Moon. On the far right is the projected number of kilometer-sized near-Earth asteroids in each of those velocity bins, larger than kilometer diameter, so that's 27 of them, I think, with the closest projected C-type or water-rich asteroid way down there near a little over 4 kilometers per second. So that's interesting, because if you are flying from low Earth orbit out to geosynchronous orbit to put up a communications satellite, that's about what you require. In other words, landing on a carbonaceous asteroid has about the same propulsion requirements, the best ones, has about the same propulsion requirements as putting a communications satellite in geosynchronous orbit. So don't tell me that this is too hard. Now, I'll talk briefly, and I'll show some view graphs that I don't have time to get much into, to let you know they exist, so I can, if you request them, I'll provide them to you. Talk a little bit about planning missions to go to these asteroids and to use water from near-Earth asteroids as propellant. Now, what's the philosophy behind this is really simple. Nothing is more expensive than mass lifted off of Earth. The cost of lifting mass off the surface of the Earth is, if you take sort of an average of all the existing large boosters, several $1,000s a pound. If you take the America's great contribution to space technology, the space shuttle, which was designed as a reusable booster to bring costs down, the cost per pound of payload is, of course, higher. What we're talking about here is making available in near-Earth space and at the sites of future human activities between the Earth and Mars, propellants that do not have to be lifted from the surface of the Earth. Water. And I submit to you that water itself is a propellant. It's certainly possible to think of electrolyzing water using solar arrays to produce electric power, electrolyzing water into hydrogen and oxygen, liquefying them, and using them for hydrogen-oxygen propellant. But I'm going to show you some mission scenarios now in which the propellant is water. You simply land on an ice-bearing asteroid, melt it, filter it, and there's your water. How do you use water as a propellant? There are two major ways of doing it. It doesn't exhaust the list. One is called nuclear thermal propulsion, where you have a nuclear reactor. You simply run liquid water through the nuclear reactor, it boils, and you eject a column of steam. It's called a steam rocket. And some very interesting studies of steam rocket performance have been done by Tony Zucchero at the Idaho National Engineering Lab, showing that you can retrieve, using locally derived propellant, you can even retrieve samples, huge samples of material from Earth-crossing comets. So these asteroids are just duck soup by comparison. The other kind of steam rocket uses a solar collector, a large inflatable collector which focuses sunlight down onto a thrust chamber, which is made of a refractory metal such as rhenium. Liquid water is run into the thrust chamber, which is heated to extremely high temperatures by being at the focal point of the mirror, and shoots out the rear end. And there you have a large amount of thrust, a steam rocket, which is a solar thermal steam rocket as opposed to a nuclear thermal rocket. Okay, now we're going to look at some scenarios for round-trip missions to some of these near-Earth asteroids. There's a lot of technical stuff here. Love it or leave it. You know. Next transparency, please. Here are the different kinds of models we considered. Direct launch from Earth, we compared it to several different scenarios for getting material from the Moon and from near-Earth asteroids. And the numbers, 1 through 5, are directly comparable. They make similar technological assumptions. For example, M3, M stands for Moon, 3 means that all of the velocity changes are propulsive, and they used lunar-derived liquid oxygen for all the burns above Leo. A3, all delta V's are propulsive using asteroid-derived liquid water for all the delta V's above Leo, and so on. Items 3 and 5 are especially important. M, of course, remember, is moon, A is asteroid. 5 uses, for return to the space station, uses aerobrakes made out of lunar material to decelerate the spacecraft as it passes through the upper fringes of the Earth's atmosphere and help it match speeds with the space station. K5 uses an aerobrake made from asteroidal material. Okay, let's move along here, and let's just do a basic comparison of the simplest scenarios. Direct launch, single mission. You go out to the surface of the body and you come back. You compare direct launch from Earth to the space station to launch from Earth to the moon to retrieve materials to return to the space station, and compare that to launch from Earth to a near-Earth asteroid to return materials to the space station. Next transparency, please. Okay, here we have them. The E1 there, launched from Earth, returns a unit of mass to low Earth orbit. And that same launch vehicle can put 0.33 units of mass in geosynchronous orbit or 0.4 units of mass in highly eccentric Earth orbit, which is an orbit that grazes the tops of the radiation belts and goes out perhaps halfway to the moon. The asteroid missions listed on there that are capable of returning material to the space station give a mass return of 3.7 units in the all-propulsive case and 24.3 units in the case where they use aerobrake. And notice that the highest return actually is to highly eccentric Earth orbit. The reason for that is that you don't have to do the entire deceleration into low Earth orbit, and your next mission can depart from an orbit that already virtually reaches escape velocity and doesn't have to leave from the space station. So it makes a lot of sense to have a base in highly eccentric Earth orbit, perhaps one that is lunar anchored by lunar tidal forces for the orbital period of a few days. Notice that the numbers here are assume the same launch from Earth. Okay? So a launch vehicle that from Earth will provide 1 ton to the space station will, if you send it to the asteroid first and retrieve asteroidal material and bring it back to the space station, it'll return 16 to 25 times as much material to the space station. Well, that's sort of amusing. See, not only is the outbound energy requirement to get to these things very modest, but the return from them is enormously better. To return from a near-Earth asteroid to Earth, you usually just have to kick yourself off the surface of the asteroid, modify your orbit just a tiny bit so that it will hit the Earth's atmosphere, and then hold your breath. The delta V requirement to get back from the moon is about 3 kilometers per second. The delta V requirement from the asteroid 1982 DB is 0.06 kilometers per second, and there are cars out on the street that are capable of 60 meters per second, roughly. I hope not in downtown Washington. So there's a tremendous difference in what you can bring back once you've landed. So I've already made the strong point that it's easier to land on these near-Earth asteroids than on the moon. Now I make the much stronger point that once you've landed, you can bring back enormously more material from the near-Earth asteroids because you don't have to fight a deep gravity well to get off them. Okay, we can just run through the next few fairly quickly, and I will summarize them again. This is for sending one mission out, returning propellant on the first trip, and then using all of that propellant returned on the first trip to fuel an armada of vehicles which go out for one more trip. And then each one of these vehicles is assumed to have an operational lifetime similar to that of a geosynchronous orbit communications satellite. The mass payback we get then, the number of tons of useful material we end up with at our Earth orbiting base, per ton that we had to launch from Earth, comes out to be 35 to 115. And these are for missions to an average of the dozen best known near-Earth asteroids. So you can have a leverage of a factor of 100 in the amount of mass you have available for use in space if you go to the near-Earth asteroids and return mass from them instead of simply launching from the ground. If you want to have expeditions departing from Earth orbit to go to Mars, the cheapest place to get the propellant might not be Earth. It might be near-Earth asteroids. If you're interested in building constellations of solar power satellites around Earth, the cheapest place to get the metals from might very well not be the Earth, and not the Moon either, but near-Earth asteroids. 100 to 1 mass payback. The next transparency gets on with a little more detail. Here we take a known black carbonaceous near-Earth asteroid, 1977 VA. And with this sequence of missions, you can show a mass payback of 28 to 1. Next one, please. Here is what happens if you use the fuel from the first trip to refuel an armada of vehicles and send them out and do 3 round trips. You see the whole program occupies 15 years. You get a mass payback of 52 to 1. And this is the best known carbonaceous near-Earth asteroid. The best one that really exists is probably a lot better than that. Okay, let me skip to the conclusions. 1 or 2 more transparencies down the stack. That's it. The basic conclusions are this. First of all, the mass payback that can be realized from using asteroidal resources is much higher for good near-Earth asteroids than for the Moon. A one-trip scenario to the Moon and back has a mass payback that is less than 1. You need a fully mature, complicated transportation system in order to even break even with with chemical propellants exporting materials from the Moon. The best you can do is about 2.4 to 1. These missions turn on at about 50 to 1 and go up to well over 100 to 1. Second, highly eccentric Earth orbit is the best staging orbit for near-Earth asteroid resource use. It also turns out to be better for lunar resource use than using the space station. Third, there are very large benefits to the use of asteroid-derived water as a propellant. Fourth, there are, although I didn't talk much about it, the charts there documented also that there are further benefits to be gained from using an asteroid-derived aerograte to get captured into orbit around the Earth. A low-performance solar thermal steam rocket is very attractive, and I talk solar thermal, Tony Zucchero talks nuclear thermal. You can have it either way, depending upon the legal environment in which you operate. Number 6, multiple round trips are feasible and advantageous. Incidentally, these steam rockets operate at such low temperatures that there's essentially no erosion of the nozzle throat, and you can use the nuclear rocket for a long time. This is very undemanding. It's a cool rocket. These benefits, which we demonstrated first for round trips to average near-Earth asteroids, hold up very well for real round trips to a real known black carbonaceous asteroid. Using the propellant returned to fuel armadas of retrieval vehicles works very well, and it's advantageous to do the first refueling in low Earth orbit. Another point I didn't develop much. But it underlines the importance of the discovery and the spectroscopic characterization of C-type near-Earth asteroids, the carbonaceous ones. I submit to you that the C-type near-Earth asteroids, because of their water content, are the most attractive resource in the near term in the solar system. They enable a wide range of future human activities in space, and they permit a vast increase in the scale and scope and the level of ambition of future space activities, while lowering the cost of launching from the surface of the Earth, because most of the mass you use on these missions is no longer lifted from Earth.